Today's talk is on x86 disassembler internals. Basically, it's about how disassemblers work, focusing on the x86 instruction set. I'm Richard Johnson. I work for iDefense Labs. I also do some research with the No Login Research Group and the Uninformed Research Journal. iDefense, if you don't know, is a company that does a lot of vulnerability research and has a program where we purchase security research from individuals like yourselves. We can talk about that later. But purpose of this talk is to basically introduce the core components of a disassembler, refresh some binary format parsing concepts, explore programmatic disassembly analysis methods, as in writing your own code to do your own disassembly. And hopefully, at the end of this, you'll be inspired to take on the task of developing your own binary analysis tools and disassembly tools as well. Basic layout's going to be a discussion of the core architecture, followed by some basic disassembly analysis methods, including some code examples. And then we'll talk about some more advanced stuff, including methods for path analysis, such as loop detection and data flow analysis through various methods, whether it be static or emulation-based. So, disassemblers, they basically are used to decode machine language back into a human-readable form so that we can read the code at a very low level after the compilers produced an output form from a high-level language. Reverse engineering has been around forever in many different forms, but in the software world, we use a program, disassembler, to understand an unknown or closed system that may not be open source or may not have sufficient documentation for us to understand the algorithms and the inner workings of that program or protocol. Reverse engineering has a number of applications, whether it be interoperability. There's people who reverse engineer on OS X, for example, or on open source platforms to create software that's compatible with iTunes or other proprietary formats. Copyright evasion, of course, some people started their reverse engineering and cracking software, technology theft, and software security, finding vulnerabilities. The goal of reverse engineering is generally to gain a higher level understanding of something that you don't have much information about. And the low-level disassembler is powerful, but it's very limited in instruction decoder in the sense of, it's powerful because it gives us a readable representation of code, but it doesn't really do a lot of work for us off the bat. So it's a pretty tedious process to manually comment all your code and manually discover every little bit of functionality from a line-by-line assembly representation. Some more advanced disassemblers, such as IDA and HTE, Bastard from Mammon, they're capable of doing a little bit more work for us. They can understand the format of various binary executables. They can detect function prologues and calls to locations in code. They can do some cross-referencing on static data locations and code references of immediate values. And I'm about to show you that now we can take it a little bit further and also recognize structures and objects in code, which is a very useful capability when you're dealing with an unknown piece of code and you don't understand how the data is represented within that program as it gets processed and flows through the program. So the core architecture of a disassembler essentially involves an instruction decoder that is essentially described in an architecture manual, the mnemonic representation of the actual machine code opcodes that are produced by the compiler. And so, you can read these manuals and understand the lookup tables that you need to create. And so when you go through parsing the binary code, you perform these lookups and decode the instruction opcodes and then the operands and the flags, and we'll take a look at that here in a second. In addition, the more basic functionality of parsing file formats is pretty crucial, so you can pull symbol information and understand where static data is kept in the file and where text data is kept in the file. So maybe you can be intelligent about how you represent that data in your disassembler. So real quick, IA32 is just considered to be a more complex type of processor. Its instruction set is a little more complicated. There's variable ways to do the same task. Rather than only have a add instruction, they have an add and a multiply and a divide. There's multiple methods to create the same functionality within the processor itself. RISC architectures tend to be a little bit easier to write disassemblers for. They have a reduced number of instructions and therefore generally only have one table to process as opposed to in an Intel instruction set, you have multiple length opcodes. So whether it be 1 byte, 2 byte opcode, 3 byte opcode, you're gonna have different tables and you just have to do a little more parsing. It's not a lot of work programmatically, but more so in building the tables and just having more flags to process. So this is kind of what a typical disassembler's internal tables might look like for decoding an instruction from byte form back into the mnemonic. Essentially, this, like I said, there will be multiple tables. This one is the 1 byte opcodes, and they're just indexed by their hex value into this table. And so you'll see that opcode 0 or 1 or 2 looks like it's going to be an add. And then following that, you see these two columns, the ones beginning with AM underscore. Those are opcode, operand value flags rather. And below these defines kind of describe what those operand flags mean and how you process the operand from the bytes that are following the original opcode that you're actually decoding. So in the case of an add instruction, you're going to have two values following it. It may be a register, it may be an immediate value, and depending on whether it's going to be a register or immediate value, you're going to have a different opcode, and the flags are going to be different for the operands. So I mean, it's pretty straightforward. It's just a lot of table lookups and continually looping through this processing. And yeah, so to break it down a little bit, you parse the opcode prefix by first looking at the first byte of the instruction that you're currently on and decoding. Multi-byte opcodes will still have, of course, the first byte being one of 0 through 255, and depending on which one it is, there will be significant opcodes that say, okay, well this one is actually the beginning of a 2-byte opcode or a 3-byte opcode. So you determine which table you're going to do your opcode lookup in, and then actually just straightforward index by the opcode number. And then you parse the addressing method of the operands, whether it be register, immediate, or displacement value from another register, and the size or type of the data that it's going to be using in that opcode. So the two primary executable binary formats that we deal with, or maybe three now, if you want to include OSX, so would be ELF on Unix platforms. Most Unix platforms support ELF these days. PE file format, or PE-COF, would be the standard Windows file format, and Mach-O would be the OSX file format. I'm going to give some pretty detailed information on how to process each of these PE and ELF binary formats, but I'm going to kind of skip over it a little bit because I've added a lot of content to the latter portion of these slides. So we'll get a brief overview of the executable formats, and then you can look at the actual code samples in the slides later to get a better idea of how you parse symbols. But all executable binary formats have certain properties in common. Their purpose is to tell an operating environment how to load and possibly link this file into the running operating system so that you can take it from a binary image into a process image and allow it to execute by setting up memory segments and relocating symbols and so on. So the kernel and the userland actually have two different views of a binary. The kernel understands it as a series of memory segments that need to be initialized with different permissions, whether it be a readable and executable segment or a writable segment for data, etc. And for dynamically linked binaries, there's an interpreter in userland that performs the runtime linking phase, which actually allows you to use shared libraries and fix up the import tables, whether they be the PLT or GOT in ELF or the actual import tables in the PE file format. And the linker views the file a little bit differently. Rather than simply understanding that there are memory segments with different permissions, it understands that there's significance to certain types of data within that file. There's various sections. Some sections hold symbols. Some sections hold, again, static data. Of course, the text section holds the actual code of your program. And so the linker itself usually parses a certain set of sections to understand which imports are going to be required and what relocations are going to be required to finalize the process of allowing this program to execute from beginning to end. So ELF, it's been around quite a while. Like I said, I'm going to kind of skip over this a little bit, but it was originally in Server 4 Unix in 1989. And it includes all the significant information I just mentioned, section headers, symbol tables, string tables, dynamic linking information. And when we're writing disassemblers and code analysis tools, binary analysis tools, it's important that we retrieve as much of the information that's there as possible and use it in cross-referencing and use it in contextual hinting and stuff when you're actually displaying that binary. So just real briefly, ELF objects are composed of an ELF header, which defines the overall structure of the file. It has pointers into where the program header table is, which is what the kernel will interpret as the memory layout information, and also section header tables, which is what the linker will interpret for its various fix-ups and relocations. And then, of course, object code and specific symbol tables. And then the ELF header looks like this. As I said, I'm not going to go into too much detail here, but it essentially tells the operating system at load time what this file has been output for what type of system and whether or not it's appropriate to be running on this particular operating system. Basically, in the kernel, your ELF loader or all your binary loaders are actually in a linked list, and it goes through a kind of a drop-through system to do some checking if this header at the very beginning of the file is describing a file that's supposed to be processed by this particular function. And if not, it'll return it and it'll go back to the next one. And that's why you have the magic OX7F ELF at the very beginning of it, so it can check the magic header on that as well. Then the section header table begins simply by taking the base address of the mapped ELF file and adding the ELF section header offset value, which is part of that ELF header we just saw. And the sections are described through this structure right here, which has a symbolic name, significant types, flags, the load address, the file offset, etc. And again, I have a lot of code in here. This is essentially code that will allow you to process this, but I have example code too, so we'll kind of go over this part of the code a little bit later. PE, of course, has the same significant information that tells the operating system how to load it as well. It's a little bit more of a cumbersome to parse. It's not quite as straightforward as ELF, where it's typically an ELF. You basically take the base address plus an offset to whether it be a section header table or the program header table, and you multiply it by the number of the index of the section header that you want to address. Whereas in PE COF, you tend to have to follow a more indirect path to actually get those offsets that you're looking for, because it actually is composed of multiple different little types of file formats, including a DOS stub that runs in native 16-bit mode. It includes a COF file header, which, funny enough, has things like pointers to a symbol table, which is not actually used in PE COF. It's a conglomeration of a few different file formats over the years, and it just ends up being a little more of a pain to deal with. But let's see. So the final component of a disassembler that's going to be useful to reverse engineer is going to be the disassembly analyzer. And this is where really a lot of the work comes in and takes that parsing capability and turns it into a representation, doing some work to tie all these symbols together within the code references, and is capable of actually bringing meaning to what all this readily available information that's there means to us. And it does this by parsing all the information, building a database, and then as it represents, as it displays this to you, as it outputs it to you, it'll continuously be doing lookups in its own database of, is this a symbol that we know? If it is, maybe we should display the symbolic name rather than just the address. It's much more meaningful to us. It's pretty immature area. It's definitely an imperfect science. You can do a lot of programmatic analysis on a file, but you're never 100% sure of the accuracy of that analysis, because there's many tricks that can be used to defeat debuggers and disassemblers, and we'll take a look at a couple of those as well. But the more powerful it becomes, you start to draw the line between static analysis and how much of this code you're actually trying to emulate or run to determine the actual outcome of a certain code path or